We've all waded through the dense math for filters and systems analysis, transfer functions, Z transforms. It feels like pure number crunching.
Yeah, lots of polynomials, complex algebra. It looks like something you'd just feed to a computer.
Exactly. But today we're taking a different route. There's actually this really elegant graphical shortcut.
That's right.
We're going to see how you can basically map out a system's entire frequency behavior, its gain, its timing, just by looking at where a few points are on a graph.
That's our goal for this deep dive. We want to interpret the frequency response that's dj omega for discrete time, or hj omega for continuous time purely geometrically.
So just by looking at the locations of the system's poles and zeros in the complex plane, the S-plane or the Z-plane.
Precisely. Just those X marks for poles and O marks for zeros tell you visually what the system does to different frequencies.
Okay, quick refresher then. The transfer function HZ, that's like the system's full recipe, isn't it?
It is. But to know the output, the frequency response, you have to evaluate that recipe, that function, along a specific path.
Right. For digital stuff, discrete time, that path is the unit circle in the Z-plane, where Z equals uj omega.
And for continuous time systems, it's the imaginary axis in the S-plane, where S equals g to omega.
So the geometry we're talking about, it all happens right on these contours.
Exactly. And the first step is remembering that these transfer functions, well, the rational ones anyway, they can be factored.
Factored, you mean broken down?
Yeah. You break the numerator polynomial into products of simpler terms, like zia. The zias are the roots of the numerator. Those are the system's zeros.
Okay, the zeros are in the numerator.
And you do the same for the denominator. You factor it into terms like z gamma. The gamma are the roots of the denominator. Those are the poles.
Okay. So you have products of z minus 0 on top and z minus pole on the bottom.
Correct. Now here comes the graphical leap.
This is the key parts, right?
Yes. Remember, we evaluate the transfer function on the unit circle, so we replace z with ej omega, which is just a point on that circle.
So that term zj omega becomes ej omega z.
Exactly. And subtracting complex numbers like that, well, geometrically, it's a vector.
A vector? How so?
It's an arrow drawn on the complex plane from the location of the 0 omega to the point ej omega on the unit circle that we're currently looking at.
Oh, I see. So for every 0, there's a vector pointing from it to our frequency point on the circle.
And the same for every pole. A vector from the pole location gamma to that same point, ej omega.
Okay, so we have all these vectors flying around. How does that help?
Well, think about what a complex number represents. It has a magnitude and an angle.
Right.
The magnitude of that vector, ej omega z, is just its physical length. You could measure it with a ruler on the graph.
Its length. Okay.
And the angle of that complex number is the angle that vector makes with the positive real axis. You could measure that with a protractor.
So we've turned algebra into geometry,
Yeah.
lengths and angles.
Precisely. That's the shortcut. No more complex polynomial evaluation needed for intuition.
So if I want to figure out the gain, the loudness, at a certain frequency, the magnitude response, I just need to know the lengths of these vectors.
You got it. The overall magnitude response is just some constant gain factor, k, multiplied by a big fraction.
And that fraction involves these lengths.
Yes. It's the product of the lengths of all the vectors from the zeros divided by the product of the lengths of all the vectors from the poles.
Wow. So gain is literally just a ratio of distances on this complex map.
It is, which gives us this really neat push and pull intuition.
Okay, let's unpack that.
Right.
What happens if our frequency point, ej omega, moves really close to a 0?
Well, the zero vector link is in the numerator, right?
Right.
So as ej omega gets closer and closer to the 0, 0, the length of that vector gets really, really small.
And a small number in the numerator means the whole fraction gets small.
Exactly. The overall magnitude response omega gets pulled down, attenuated. So zeros near the unit circle act like frequency suppressors.
They pull the gain down. And what if the 0 is actually on the unit circle?
Then at that specific frequency where omega makes ej omega land right on the 0, the vector length is 0.
Which makes the whole magnitude 0.
Correct. The response is completely killed at that frequency. That's how you make a notch filter.
Like killing 60 hertz hum. You'd put zeros right on the imaginary axis at plus and minus to j omega 60.
Or for continuous system, yes. Or for discrete time, say you put a 0 right at 0, xly, and 8, next to 1, 1.
That corresponds to the highest digital frequency, omega pi.
Right. And having a 0 there forces the gain to 0 at that highest frequency. It helps create a low-pass filter effect, smoothing things out.
Okay, so zeros pull down. Now the opposite effect, poles. What happens when EJ omega gets close to a pole location? Line it.
Now we look at the denominator, the pole vector length, the UNG omega is down there.
So as that distance gets small,
Dividing by a very small number makes the overall result very large. The magnitude response gets pushed up.
so poles near the unit circle cause amplification, resonance.
Exactly. That's where the energy peaks come from in the frequency response. Proximity to a pole means gain.
How close does the pole have to be? Does that affect the peak?
Hugely. For a stable system, poles have to be strictly inside the unit circle. But the closer a pole gets to that boundary, say its radius is 0.9, then 0.95, then 0.99.
Closer and closer to 1.
Yes. As it gets closer, the minimum possible distance between AJ omega and the pole gets smaller. This makes the resonant peak much higher and also much narrower, much more selective in frequency.
Like tuning a radio very precisely.
That's a great analogy. A pole very close to the unit circle gives you a very sharp, high Q resonance, picking out just that frequency.
Okay, so magnitude is all about distance is the ruler.
Yeah.
Poles push up, zeros pull down. Now what about phase? The timing aspect.
Right. The phase response, angle h, omega, if magnitude comes from vector lengths, phase must come from
Vector angles.
Exactly. It's the angles of those same vectors, measured relative to the positive real axis.
So how do we combine them? Is it a ratio again?
Not quite. For phase, it's additive and subtractive. The overall phase angle is the sum of all the angles from the zero vectors minus the sum of all the angles from the pole vectors.
Sum of zero angles minus sum of pole angles.
Okay.
And this phase tells us about time delay, you said.
Yes. A phase shift at a certain frequency corresponds to a time delay for that frequency component.
What happens if that phase response isn't like a nice straight line, if it's all bumpy?
That's phase distortion. If the phase isn't linear with frequency, it means different frequency components of your signal get delayed by different amounts.
So a complex sound might get smeared out in time. High notes arriving at a different time than low notes.
Precisely. It degrades the signal's waveform, its shape. That's why linear phase is often so desirable.
Linear phase means the phase response is just a straight line, like angle h j omega.
Yes. That constant slope, tau Eulers, means the time delay is the same for all frequencies. Everything stays perfectly synchronized as it goes through the system. Crucial for audio, video, data, preserving the signal shape.
And there's a term for that delay, right? Group delay.
That's right. Group delay, usually written as tau omega, is formally the negative derivative of the phase response with respect to frequency. So tau omega dash d omega.
That derivative, so it's the local slope of the phase curve.
Essentially, yes. If the phase is perfectly linear, the slope is constant, and the group delay is constant. If the phase curve wiggles, the group delay plot will show peaks and valleys, indicating where frequencies are being delayed more or less than others.
So looking at the group delay plot is a good way to spot potential phase distortion issues.
Absolutely. It directly shows you the frequency-dependent delay. One thing to watch out for with phase plots, though, are jumps.
Jumps!
Yeah, you'll see discontinuities. Some are just artifacts of keeping the phase angle wrapped within a certain range, usually a day pi. You jump by 2 pi's when you cross the boundary.
Okay, those are just display conventions.
Right. But you can also get jumps of Bay Pi Bay. These happen when the real part of the frequency response happens to cross zero and change sign. These jumps do affect the derivative, so they can make interpreting group delay a bit trickier sometimes.
Good to know. Okay, so we have magnitude from distances, phase from angles. Let's talk about designing filters using this. We mentioned putting zeros on the unit circle for a knot filter.
Right. That geometric insight is super powerful for design. You want to affect a certain frequency. Place poles or zeros near it.
Can we design filters that only affect phase and leave the magnitude alone?
Yes. Those are called all-pass filters. They have a perfectly flat magnitude response and omega everywhere, but their phase response can be quite complex.
Flat magnitude, so they don't change the loudness of any frequency.
Yeah.
How do you build one of those geometrically? What do the poles and zeros look like?
They have a very specific mirrored structure. Poles and zeros come in what are called conjugate reciprocal pairs.
Conjugate reciprocal pairs, what does that mean?
If you have a pole at some location, let's say in polar coordinates at radius dollars and angle theta, so AT, EJ, theta, then there must be a corresponding zero at radius 1 angles and the same angle to theta. So at frac 1 AJ theta.
So the zero is at the inverse radius, but the same angle. And if the pole is complex, say EJ theta, the zero is at frac 1J theta.
Well, you also need the complex conjugates for real filters. So if you have a pole pair at EPMJ theta, you need a zero pair at 2EPM EJ theta, inside the unit circle pole, outside the unit circle zero, mirrored radially.
Okay, this is special mirrored placement. That's what guarantees the magnitude stays flat.
Exactly. The contribution to the magnitude from the pole vector's length in the denominator gets perfectly canceled out by the contribution from the reciprocal zero vector's length in the numerator at all frequencies.
That's clever. So an all-pass filter is like a phase manipulator. It doesn't change the sound's frequency balance, but it changes the timing.
Precisely. Its main use is for phase equalization. If some other part of your system, like a transmission channel, introduces unwanted phase distortion, you can design an all-pass filter to introduce the opposite phase shift to cancel it out, correcting the timing issues without altering the magnitude response.
Very neat. Okay, one last big topic tied to this geometry, system inversion. If we have a system OHZ, sometimes we want to build its inverse, OHZ, 1HZ, maybe to undo the effect of a channel in communications.
Right, finding a stable inverse is often critical.
What does the stability of the inverse depend on, geometrically speaking?
Well, think about inversion. Each z is one HZ. Denominator z.
Denominator z is denominator z. The poles and zeros swap places.
Exactly. The zeros of the original system, Hz, become the poles of the inverse system, H0.
Ah, so the stability of the inverse system depends on where the zeros of the original system were located.
Correct. For the inverse system, H1z, to be both stable and causal, meaning its poles are inside the unit circle, the zeros of the original system H1 must also have been inside the unit circle.
So for a stable causal system Z to have a stable causal inverse H1, a condition must be met.
Yes. Not only must the original poles be inside the unit circle for HC stability, but all of its zeros must also be inside the unit circle.
All poles A and D, all zeros inside the unit circle. Is there a name for systems like that?
There is. That's called a minimum phase system.
Minimum phase. Why that name?
It relates to the phase characteristic. For a given magnitude response, the minimum phase system is the one that has the minimum possible phase lag across frequencies. Any other system with the same magnitude response, like one made by flipping a zero to its reciprocal location outside the unit circle, will have more phase lag.
Okay, so minimum phase means poles and zeros are all safely inside. And this guarantees we can build a stable filter to undo its effects.
Yes. If your system is minimum phase, you can create H1Z and it will be stable and causal. If even 1 0 is outside the unit circle, making it non-minimum phase,
Then the inverse system will have a pole outside the unit circle, making it unstable. You can't perfectly reverse it with a simple, stable filter.
precisely. This comes up a lot in things like modeling echoes or multipath in communications. Those physical effects often introduce zeros. If a zero happens to land outside the unit circle,
You have a non-minimum phase channel, and recovering the original signal gets much harder.
you need more sophisticated techniques than just simple inversion.
It really is quite powerful how all these concepts, gain, resonance, phase, delay, even invertibility, boil down to just looking at where those poles and zeros are relative to the unit circle or the imaginary axis.
It is. Proximity drives magnitude, angular position drives phase. It turns complex analysis into intuitive geometry.
A system's frequency fate really is sealed by its poles and zeros.
Absolutely, and that brings us back to that minimum phase idea. It guarantees stable invertibility, minimum phase lag. But think about filter design.
Yeah.
Often, to get really sharp performance, like a super steep filter cutoff or a perfect notch, designers might be tempted to place poles or zeros very close to or even directly on the unit circle.
Right, for maximum effect at that
Yeah.
frequency.
But doing that, especially placing zeros on or outside the circle, instantly makes the system non-minimum phase. You sacrifice that guaranteed stable invertibility.
Oh, so there's a trade-off.
There often is, which leads to a final thought for you to consider. When you're designing or analyzing a system, what's the priority? Are you optimizing purely for the magnitude response, getting the sharpest peaks and deepest notches possible? Or are you prioritizing the system's phase behavior and ensuring that its effects can be perfectly and stably undone later if needed? It's a fundamental design choice driven entirely by that pole zero geometry.